Hi, everybody. You've heard me say many times, the body does what makes sense. Changes in cardiac output are no different. The body pumps that same volume of blood through your body faster during exercise. This provides an increase in nutrient waste and gas exchange to sustain that metabolic activity. When the race is finished, the cardiac output, well, it decreases. In this lab, we focus on measurement and calculations associated with this amazing cardiovascular system. Remember, the cardiac output is a function of your heart rate, beats per minute, times your stroke volume, milliliters per beat. We can directly measure heart rate easily by taking a direct heart rate and listening to heart sounds, or a pulse rate by feeling distension of an artery. But measuring stroke volume directly, that would be invasive. So thankfully, we can use mathematics to estimate the stroke volume from a painless measurement, your blood pressure. So there are two measures for the number of heartbeats in 1 minute. Pulse rate feels for the distension or stretch of an artery against your fingertips. This works because that stretch occurs when blood pushes into the artery when the ventricle ejects that blood at the end of ventricular systole. Each thump against those fingertips represents one cardiac cycle. Now we can be a little extra fancy and we can use a stethoscope to listen to someone's heart sounds and count the luptups of a cardiac cycle. Either way, the number is a function of cardiac cycle. So it doesn't matter whether you choose pulse rate or heart rate, they are basically going to be the same number. Measuring blood pressure requires a tool, stethoscope and a sphygmomanometer, and some technique, but it's still not invasive. Now what we're really going to do is squeeze a blood vessel closed so no blood goes through it. Let that blood vessel open again so that blood does flow through it. Listen for a sound to appear, then disappear. So again, we are going to close a blood vessel off, squeeze it closed, slowly let the blood vessel back open again, and listen for blood flow to appear and disappear. So the question then becomes, well, how do we do this? Using your classmate's non-dominant arm, you would wrap this cuff of the sphygmomanometer around their brachial region. Close the valve of a bulb that you see here and squeeze the bulb repeatedly to inflate this cuff. This inflation would squeeze closed the brachial artery. Then we would slowly open the same valve, let the air out of the cuff gently while watching this pressure gauge and listening for sound changes. When this brachial artery pops back open, blood starts flowing through it again, but the blood flow is turbulent, like a river flowing over rocks. That sound is like a It marks the beginning of blood flow, and it is the systolic blood pressure. So systolic blood pressure is the pressure on that gauge when the sound appears. We would continue to deflate the cuff. Continue to let air out, and that turbulent blood flow settles and the sound eventually disappears. When the sound stops, we would read the number off our gauge, and that would be diastolic blood pressure. So again, when the sound appears, that's systolic blood pressure. When the sound disappears, that's diastolic blood pressure. Now note, it is imperative that blood pressure be measured on the brachial region. Why? Because pressure drops the further away you get from the heart. So this means location of blood measurement matters. And all healthcare providers use the brachial region only. A quick comparison of blood pressure and heart rate key points. You might want to pause the video here for a review. Once blood pressure and heart rate are measured, several calculations become possible. Make sure you memorize these formulas as they will not be provided to you. Cardiac output, that equals heart rate times stroke volume. Stroke volume is equal to pulse pressure times 2. Pulse pressure is equal to that systolic blood pressure minus the diastolic blood pressure. Mean blood pressure is equal to diastolic pressure plus 1/3 of pulse pressure. And the last one, the percent change in your cardiac output is equal to the cardiac output after you exercise minus before you exercised or at rest divided by the CO at rest times 100. We're going to do a lot of practice problems with these formulas. In this remote learning semester, we're going to have to pretend that we've taken data on a classmate. So here's your classmate's heart rate right here and their blood pressure. Heart rate was 59 beats per minute. They're very calm and relaxed. Blood pressure is 107/70. Pause the video here. Follow the instructions in your lab manual and use these numbers to calculate cardiac output. When solving problems, I like to work backwards. Just focus on formulas first. Write the formula that contains the term you're being asked to solve for. In this case, that's the formula for cardiac output. Look at each data point, heart rate and stroke volume, and ask yourself, do I have that data point? Do we have heart rate? Yes, we do. It's 59 beats per minute. Do we have stroke volume? No, we don't. So we're going to have to calculate it. So since stroke volume is unknown, that becomes the next formula that I write. So stroke volume is equal to pulse pressure times 2. I have to solve for it. Do I know the number 2? Yeah. But do I know pulse pressure? Is the pulse pressure reported above? It's not. It is also unknown. So since that's the unknown, that's the formula I write next. Pulse pressure is systolic blood pressure minus diastolic blood pressure. So let's do the same thing. Do we know systolic blood pressure? Yes, we do. It's reported. It's 107. Do we know diastolic blood pressure? Well, yes, we do. It's reported. It's 7. So in this last third formula here, we know systolic. We know the diastolic. There are now no missing data points. So what we are going to do is start plugging numbers in and working our way backwards. So pulse pressure is the first one we're going to work on. Pulse pressure is systolic blood pressure minus diastolic blood pressure, which means pulse pressure is going to be 107 minus 70 or 37. Now move up a step. Stroke volume is pulse pressure times 2. So now let's plug in our pulse pressure. So that means stroke volume is 37 times 2, and that's 74. So now we know our stroke volume. We can bump up a step. Cardiac output is heart rate times stroke volume. And so here, let me erase my mess. Cardiac output is going to be equal to heart rate, which is 59, that was up here, times that stroke volume we had to calculate, which is 74. And when you calculate that, you are going to get 4,366 milliliters per minute. But write this down. You might calculate cardiac output in milliliters, but you need to report it in liters. So you're going to have to do a metric conversion from milliliters to liters at the final step. So again, you might, let me rephrase. So again, you will report cardiac output in liters per minute. So if that didn't make sense, pause the slide, maybe review, maybe go back a moment or two in the video and kind of replay those steps. Same thing. This would be your classmates' data after exercise. Again, you're going to follow the same steps to calculate their cardiac output after exercise. So pause the video, follow the same steps in your laboratory manual, and get their cardiac output after exercise. So if you forwarded, let's work this one together. So again, cardiac output is heart rate times stroke volume. The first formula I wrote contains the term I'm being asked to solve for. Then I asked myself, do I know this data point? Do I have heart rate? Yes, I do. It was given. Do I have stroke volume? No. I'm going to have to solve for that next. So I write the formula for stroke volume next. Stroke volume is pulse pressure times 2. 2 is a conversion factor, I know it. But pulse pressure is unknown. So I write the formula for pulse pressure next. Pulse pressure is equal to systolic minus diastolic. In the same process, do I know systolic blood pressure? Yes, it was provided. Do I know diastolic blood pressure? Yes, it was provided. So I'm now at the point where I have complete data. I'm going to work my way backwards. Pulse pressure is systolic minus diastolic. And so if I plug in those numbers, pulse pressure is 121 minus 82. So my pulse pressure is 89. Now, stroke volume equals pulse pressure times 2. Plug in that pulse pressure of 39. So stroke volume becomes 39 times 2 equals 78. Our stroke volume is 78. Now we're going to plug that in. Cardiac output is equal to heart rate times stroke volume. Our heart rate was 71. Our stroke volume we calculated at 78. Again, when you first multiply that, you're going to get 5,538. So convert that into liters. So we would report cardiac output in this example as 5.538 liters per minute. So this was your classmate's cardiac output after exercise. Your lab manual is going to coach you through calculating percent change in cardiac output. Percent change in cardiac output is the cardiac output after exercise. Subtract off the cardiac output at rest. Divide by the cardiac output at rest. Multiply that by 100. So for this classmate, their percent change was a 26.8% increase in their cardiac output after exercise. With the review questions, apply the same principles. Write the formula that contains the term you're asked for first. Ask yourself, do you have data missing? If you have data missing, write that formula next. Keep going until your formula contains all known data points, then work your way backwards. You want to use review questions and lots of practice questions. Here's a review question. Vicky, her blood pressure is 130/80, her heart rate is 70 beats per minute, and you are asked to calculate her cardiac output. So cardiac output is the first formula we write because that's the term you're asked to solve for. Cardiac output is heart rate times stroke volume. Do we know her her heart rate? Yep, it's right there. Do we know her stroke volume? Nope, it's a mystery. So you write the formula for stroke volume next. Stroke volume is equal to pulse pressure times 2. 2 is a set number. Do we know pulse pressure? No, we don't. We're going to have to solve for it. So we would write the formula for pulse pressure next. Same concept. Do we know the terms? Do we have systolic blood pressure? Yep, we do. It's reported above. Do we know diastolic blood pressure? Yes, we do. It's reported above. You are now have a complete set of data, and now you're going to follow your formulas backwards. Another review question. This is Bob. Stroke volume is 102 milliliters per beat. Systolic blood pressure is 150 millimeters of mercury. And you're asked to calculate MBP. So this one's definitely more challenging, but we're going to follow the same steps. Step 1, write the formula that contains the term you're asked to solve for. In this case, that's mean blood pressure. I like to use the simplified formula. Mean blood pressure is diastolic blood pressure plus 1/3 of pulse pressure. Now let's ask ourselves, what data do we know? Do we know diastolic blood pressure? Nope, we're going to have to solve for it. Do we know pulse pressure? Nope, we're going to have to solve for it too. Let's write the formula that contains pulse pressure. Well, pulse pressure is in systolic blood pressure minus diastolic blood pressure. I still don't know diastolic blood pressure. I know systolic blood pressure. SBP is a known. So I'm still kind of stuck. I still got two things to solve for. Let's write the other formula that contains pulse pressure. That's this one. Pulse pressure times 2 is equal to stroke volume. Same concept. What do we know? Well, we know 2. We don't know pulse pressure, but guess what? We do know stroke volume. We can use stroke volume in the number 2 to get pulse pressure, and we are now free to work our way backwards. I'm going to start you, but I'm not going to finish this calculation. I want you to finish something challenging like this. And if you get stuck, well, email your professor. Okay, so let's plug stroke volume in for this first one. Our stroke volume is told to us it is 102. So 102 equals PP times 2. Our algebra teachers told us divide both sides by 2 to get rid of it. Pulse pressure is now 51. You can plug 51 in here. You're going to plug 51 for pulse pressure and your systolic in there to solve for diastolic. And at that point, you'll have diastolic and pulse pressure to plug in to this top formula. So again, the first formula you write is the one that is the term you were asked to solve for. Each time you have an unknown data point, write that formula next until you account for all your data points, then follow your formulas backwards. This is Tom. His cardiac output is 6.8 liters per minute. Heart rate is 100 beats per minute. Systolic blood pressure is 138 milliliters of mercury, and we're asked to calculate diastolic blood pressure. So remember, write the formula that contains the term you are asked to solve for. DBP occurs in a couple of places, so I chose to start here. Pulse pressure is systolic minus diastolic. So now let's ask ourselves, do we have that data point? Do we know systolic? Yeah, we actually do. Do we know pulse pressure? Nope. We're going to have to solve for it. So write the formula that contains pulse pressure. Well, stroke volume is pulse pressure times 2. But 2 is a known variable. I don't know stroke volume yet. So that's the next formula I'm going to write. What's the other formula that contains stroke volume? That's cardiac output. Cardiac output is heart rate times stroke volume. Do I know cardiac output? Yes, I do. It's reported above. I'm going to have to tweak it, but it's there. Do I know heart rate? Yes, I do. It's reported above. So now we can start to plug in our numbers. Same technique. Here's the deal. You report cardiac output in liters per minute, but you use cardiac output in mils per minute. So you're going to have to slide that decimal three spaces to the right. Okay? And I'll show you what I mean. So cardiac output is heart rate times stroke volume. If we slide 3 spaces to the right to get it to milliliters, that's going to become 6,800. Slide, slide, slide. 6,800 is going to be equal to heart rate, which is 100, times stroke volume. From here, you can calculate stroke volume. Follow your formulas up. Same technique. Again, if you run into difficulties, check the laboratory manual and check in with your professor to make sure you've calculated them correctly. And practice, practice, practice.